Hey everyone, in this video I want to talk a little bit about slope fields. So to start with, a slope field is a way for us to graphically represent the general solution to a differential equation. So if you remember when we were looking at the examples for first order separable differential equations, when we find the general solution, we end up with this equation that contains that arbitrary constant c. Because of that constant, and because it can represent any constant, that is a family of equations that works for our differential equation. So what that means is because that constant can be anything, we have lots of different possibilities for what the graph of our general solution could be. And because of all those possibilities, we can't just graph them all, so we use a slope field to help us represent that. So I just want to start off with a couple things to help us make sense of what's going on in a slope field. So the first thing that we need to remember is that when we're looking at a differential, dy over dx, we have to remember that this represents the slope of the tangent line. So dy over dx, that is the change in y divided by the change in x, which is the slope. So if I know a specific point that I'm looking at, dy over dx is going to represent the slope of the tangent line at that specific point. So if I know that this represents slope, what I'm going to do is I'm going to use short little line segments in my graph to represent these potential slopes of a bunch of different tangent lines at a bunch of different points. So a couple easy ones that we need to keep in mind. So let's say dy over dx is equal to 0. So that means the slope of the tangent line is 0, which means it's horizontal. So that would be a horizontal tangent line. And if that's the case, at that specific point, we're just going to use a small little horizontal line segment to represent that. Now let's say dy over dx, let's say that this is undefined. So now if dx is 0, so if my denominator is 0, we're going to end up with something that's undefined. That means the slope of the tangent line is undefined, which means that it is vertical. So on our slope field, we would just represent that with a little vertical line segment. Now our other two options, let's say dy dx is greater than 0. So now that means we have a positive slope for the tangent line. And we just want to represent that with an appropriate increasing little line segment. So let's say that the slope is 1. So that means that my line segment is going to be increasing at that 45-degree angle. If I have a slope that's less than 1, I would want to represent that appropriately. I can adjust it. It doesn't need to be exact, but we want to accurately represent it as best we can. And the last one, if dy dx is less than 0, so now we have a negative slope. And again, we just want to appropriately represent that. So let's say our slope is -1. That means our little line segment should be going down at that 45-degree angle. So now we're going to pick out a bunch of points. We would figure out what dy over dx is equal to, and then we're going to use these little line segments to represent the slopes of the tangent lines at all of those points. All right, so now let's take a look at an example just to work through that process. Okay, so here's my example. I have dy over dx is equal to -x over y. So this is a separable first order differential equation, and I want to use a slope field to represent the possible solutions for this differential equation. So to do that, we need to pick out sort of a range of values for the points that we want to use. So I'm thinking let's just do +3 and -3 in both the x and the y direction. And then at each of these points, we're going to use a little line segment to represent what the slope of the tangent line would be at that point. One thing that can really help out is maybe using a little chart to keep us organized. So we have our x and our y value, and then we're going to do dy over dx, which we'll evaluate using the differential equation. Now I don't have to do this for all of these points because what we're going to notice is there's going to be some certain patterns. So for example, if x is 0, so that means I'm going to be along the y-axis, it doesn't matter what y is because 0 divided by any of these y values, I'm going to end up with 0. So the numerator here would be 0, y can be anything, and I'm going to end up with a slope of 0. So for all these points along the x-axis, the y-axis, we're just going to represent that with little horizontal line segments. Now notice the only one I didn't put in here is the origin, because at the origin it would be 0 divided by 0, which means that we have a vertical tangent line. And that brings me to the next one. So let's say for any of these other points along the x-axis, that means y is going to be 0. So now x in the numerator doesn't matter what that's going to be. If I'm trying to divide by 0, that means we have an undefined slope. So now undefined, so that means that all of these are going to be little vertical line segments. So our tangent lines at each of those points would be undefined. Now we can go through, we can start thinking about some of our other ones. So let's just make our way through here. Let's say x is 1. Then if x is 1, and that means we're going to be here, the vertical line x equals 1. And now if we take a look and if we plug in these y values, let's sort of see what we get. So for example, if y is also 1, so that's going to be -1 over 1, so we get a slope of -1. So at this point, 1, 1, it's a slope of -1, so I'm going to use a little decreasing line segment, sort of at that 45-degree angle to represent that. If I go up to y equals 2, now we're going to have a slope of -1/2. So at this point, I'm just not going to make it quite as steep. And up here at 3, that's going to be -1/3. Again, so a decreasing line segment, but just doing my best to try and represent what that slope looks like. All right, so now if I go over to 2 and sort of use that same process. So now at 2, x equals 2 divided by 1, that's going to be a slope of -2. So at this point, slope of -2, so that's a little bit steeper than -1, so just trying to represent that. 2 over 2, that's a slope of -1. 2 over 3, a slope of -2/3, and so on. Now if I move below the x-axis, so now my y values are going to be negative, so let's say we have 1, and then my y value is -1. If I plug that into my differential equation, now this is going to be a slope of +1. So at this point, 1, -1, a slope of +1, we want to be increasing, sort of at that 45-degree angle. All right, here at -2, that's going to be a slope of +1/2. So not quite as steep. Here we have a slope of +1/3, kind of leveling out. So I'm not being extremely accurate, but again, we just want to represent these little tangent lines as best as we can. I'm going to go through, I'm going to finish up each of the tangent lines, and then we'll take a look to see what we have. Okay, so I went through and I finished up the rest of the points, putting in little line segments to represent these slopes at each of these tangent lines. As I talked about in the beginning, we can take a look at when y is equal to 0 or when x is equal to 0 to notice some patterns. As I was finishing these up, I noticed another one that can be very helpful. So based on what we had for our equation, it's x over y. So whenever x and y are the same value, that means we're going to have a slope of either +1 or -1. So along these diagonals here, at each of these points, we have that slope of positive or -1. Here those are all -1, and here these are all +1. So we have that 45-degree angle. So now take a look at that slope field. This represents the entire family of equations that work for this differential equation. The last thing I want to do is draw in one of these possibilities, or we could draw in multiple if we wanted to. So what I'm going to do is I'm just going to go to a point I'm going to pick out one of them, and then I'm going to work my way left or right around following the slopes of these tangent lines. So why don't we just go here at the point 0, 2. Now just kind of following along with all the tangent lines we have. I'm going to do my best to make this a nice smooth curve. But as you can see, as we move to the right, we start to slope down. It gets steeper and steeper. So now it starts to level out as we make our way back. And now it's going back up, just following along where these slopes are. And there we go. So I did not do a very good job of keeping this nice and smooth, but that's what one of these possible solutions would look like to this differential equation. Now let's just solve this, take a look at what our general solution is so we can verify that that's what it's supposed to look like. So separating the x's and the y's, we'll have y times dy is equal to negative x dx. And taking the integral of both sides, using our normal antiderivative rules, we'll end up with y squared over 2 is equal to negative x squared over 2, and then our arbitrary constant plus c. So we have an x squared and a y squared. So I'm going to put those both on the same side of the equal sign. So if I add x squared over 2 to both sides, we have x squared x squared over 2 plus y squared over 2, and that's equal to a constant. And these are both over the denominator of 2, so why don't we multiply the entire thing by 2? So x squared plus y squared. When I multiply this constant by 2, because it's arbitrary, it's not going to change, or it doesn't matter, in other words. So we end up with x squared plus y squared is equal to c. Hopefully we recognize that equation as the standard form equation of a circle with a center at the origin, which fits with what our slope field looks like. Our arbitrary constant here, this would represent r squared, or the radius squared. So for example, if I let my constant here be 4, that means my radius would be 2, which would represent the circle that we drew in. If we let our constant be some other value, we would end up with a different circle. So that's what our slope field represents. So using our differential equation, taking a look at the slopes of the tangent lines at a bunch of different points, representing those with little line segments, it gives us this big, broad idea on what all of these equations look like as solutions to this differential equation.